Hello, my name is Jesse Terrell Perez, and I'll be giving an oral presentation over the future of semiconductor materials. Quick background on what a semiconductor is. Materials that are neither good electrical conductors nor good electrical insulators, such as plastic and metal, respectively, are called semiconductors. Common types include silicon, germanium, and gray tin, where germanium was more commonly used before it was replaced by silicon. Semiconductor of today. Silicon is the most used semiconductor for discrete devices and integrated devices. Your computer has silicon in it, and pretty much every other electronic device you have. As a semiconductor, silicon is used to make transistors, for which amplify or switch electrical currents and are the backbone of electronics from radios to iPhones. Doping methods have been refined, which make silicon a great material to create p-n junctions, and I'm sure you're all aware of how important p-n junctions are. This point will become important later when I go over limitations of my future technology. So, limitations of silicon. For those of you not familiar with Moore's law, it states that the number of transistors in a dense integrated circuit doubles approximately every 2 years. Ever since Moore's prediction, the industry has seen fit to beat this trend. By his original estimation, there should be 100 to 200 million transistors on the highest end state-of-the-art applications. Today, the real number is close to 2 billion. Industry has steadily outpaced his prediction. But can this trend continue indefinitely? In short, no. Increasing the capabilities of modern chips is often simplistically boiled down to how many transistors can fit into one piece of semiconductor. This is why the biggest names in semiconductor production, including Intel and AMD, are constantly trying to shrink the size of transistors down. However, this shrinking can only go on for so long before it becomes either impossible to make transistors smaller or no longer financially viable to do so. This is where we come to one of the looming problems on the horizon for silicon. Possible replacements. There are many possible replacements for silicon as the next generation of semiconductor materials, some of which include diamond, carbon nanotubes, graphene, and lasers. These are just a few of the interesting and promising technologies that could be possible candidates to replace silicon. However, each of these technologies bring their own set of challenges that must be overcome before they're ready for the prime time. Quick mention, semiconductors have been produced from graphene. The result is a hybrid material which acts as a semiconductor and is just 1 micrometer thick, hundreds of times thinner than a silicon semiconductors in use today. Their ability to conduct electricity can be controlled by temperature, light, or the addition of other atoms. One big drawback is in producing enough material to make it a viable option, as its production methods aren't really defined yet. This is why we'll be going over diamond mainly in this presentation. So why diamond? Here's a comparison of diamond with some of today's most popular semiconductor materials. As can be seen, diamond really is an amazing material. It's incredibly strong due to its 3D structure and covalent bonds, near transparent, and has a high thermal conductivity. The thermal conductivity is over 14 times that of silicon. It makes it a great material for high power applications. However, as can be seen, diamond has a fairly high band gap, which makes it a good electrical insulator. This can be both useful and problematic for electrical devices. The insulative ability allows for larger voltages and smaller leakage current, while the lack of conductivity means that electricity will not flow. This is where doping comes to play. In the same way that silicon uses doping for its p-n junctions, diamonds will have to do the same thing. So a comparison of intrinsic material thickness needed to hold off 10,000 volts. Where diamond really really shines is that it far outperforms any other material in terms of its ability to insulate very high voltages across very thin layers of material. The lower the insulation strength, the more base material you need to start with, which is a big issue in wide bandgap semiconductors are already at least 10 times the cost of silicon. More importantly, the slower the device operates, which is why in the case of power semiconductors, 6,500 volts appears to be the ultimate practical limit of silicon insulated gate bipolar transistors. Advancements. We were once relegated to the amount of diamond we could pull out of the ground, making the thought of using diamond as a replacement material an expensive one. However, since real and synthetic diamonds are chemically indistinguishable, the world supply of diamonds will no longer be determined by the amount we could pull from the Earth's crust, but by the size of the market of the synthetic diamonds, which would explode if diamonds started to be used in electronics. Over the past 10 years, there have been major advances in the production of diamond by chemical vapor deposition. Today, there are several leading material growers offering extremely high quality diamond materials in a single crystal, polycrystal, and nanocrystalline forms. They can also create up to 200 millimeters wafers. Synthetic diamonds' properties make them perfect for advanced applications. We went over some of the properties earlier, but here's some extra ones as well. They have the world's highest known they are the world's known thermal conductor, a wide electronic band gap, which carries a low current even under high voltage, low thermal expansion, the world's highest resistance to shock, high electrical carrier mobility, broadest electromagnetic transmission spectrum in the world. As you can see, the diamond truly is an amazing material with lots of potential. Diamond's hurdles and future work. So if diamond can be doped and potentially make better semiconductor devices than silicon, why has it not been done yet? The answer lies in the ability to make the p-n junction of diamond. Making an n-type or p-type doped diamond is not a challenge as of recent, but making a piece of diamond that contains both close enough to create a p-n junction is very challenging. And this is where the next breakthrough will have to come from if diamond is to be realized. However, there is a little light at the end of the tunnel. There is some recent advancement by Professor Matsuko Hato, along with National Institute of Advanced Industrial Science and Technology. He has made a lateral p-n junction on diamond, which has then been created into a JFET prototype. However, there still remains a lot of work to be done in refining the doping process before it's ready to replace silicon in any capacity. But if it is refined and done, it could usher in a new era of electronics. So summary. Silicon has the problem that things can't keep getting smaller and smaller because at 22 nanometers, the technology will reach the point where there are just a few atoms of various materials doing the work. At those levels, quantum effects begin to show themselves in extremely pronounced ways. In addition, manufacturing limitations become real as they require almost completely perfect materials for features that small, which make it financially impractical. Diamonds have very desirable properties for high thermal conduction, low thermal expansion, high resistance to shock, and high electromagnetic transmission spectrum. Diamonds can be synthetically made, not solely relying on material on the ground, which makes it much cheaper. Diamond microchips could handle high power signals that run ultra hot without requiring conventional power hungry cooling systems, and since the synthetic diamonds could be created at a fraction of the cost of the natural diamonds, this becomes a very viable product for technology companies. It also has a role that could be played in a power transmission. And here's my sources. Feel free to follow them and check out the information I got. If you have any questions, shoot me a comment and I'll answer them to the best of my ability. Thanks for watching.